March 10th, 1945. The west bank of the Rhine River at Rhine, Colonel Harvey Fraser stood knee-deep in 40-degree water, shouting orders over the roar of German artillery that exploded 200 yards upstream. His hands, numb from the cold, gripped the steel pin that would connect the 7th pontoon section to the 6th. Around him, 40 men from the 291st Engineer Combat Battalion worked in organized chaos, assembling a floating bridge that would carry 30-ton Sherman tanks across the Rhine in less than 32 hours. 3 days earlier, the Ludendorff Bridge, the only standing bridge across the river, had been captured intact by sheer luck. But luck doesn't last. Fraser and every engineer in the Rhine Valley knew the old railroad bridge couldn't hold forever. The Wehrmacht had already tried to blow it twice. The structure groaned under the weight of every Sherman that crossed. If it collapsed before they finished the pontoon bridges, 25,000 American troops would be trapped on the far shore with no reinforcements, no supplies, and no way back. This wasn't the first river Fraser's battalion had bridged under fire. They'd crossed the Ruhr in February, the Ahr River 2 weeks ago. But the Rhine was different. It stretched over 1,000 feet wide at Remagen. The current moved at 8 feet per second, fast enough to tear a pontoon loose and send it tumbling downstream like a child's toy. And unlike those earlier crossings, this one had to support an entire army. Not just infantry and supply trucks, but medium tanks weighing 30 tons each, tank destroyers, artillery pieces, and the constant stream of vehicles that kept 25,000 men fighting. The mathematics were brutal and precise. Each M2 pneumatic pontoon could support roughly 2.8 tons when properly inflated. A Sherman tank weighed 30 tons. That meant each tank required at least 11 pontoons beneath it, spaced at intervals calculated to prevent the bridge from bowing under asymmetric loads. Too few pontoons and the bridge would sink. Too many and you wasted time assembling equipment that could have gone into building a second bridge. Fraser's engineering tables, printed on waterproof cards tucked inside his jacket, gave him exactly 14 minutes per pontoon section under ideal conditions. But these weren't ideal conditions. German artillery had the range. Luftwaffe jets, rare but deadly, made strafing runs twice a day. And the river itself fought every connection, every pin, every anchor cable with relentless hydraulic force. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem facing Allied engineers in March 1945 wasn't new. Armies had been building floating bridges for over 2,000 years. What was new was the speed required and the weight those bridges needed to carry. Modern mechanized warfare demanded solutions that ancient engineering simply couldn't provide. In 480 BC, Persian engineers serving Xerxes the Great built a pontoon bridge across the Hellespont using 674 boats lashed together with flax cables. It stretched over a mile and allowed Xerxes to move 100,000 troops from Asia into Europe. Contemporary historians called it a marvel. But here's what matters for understanding 1945. That bridge took 3 months to construct and collapsed twice during assembly when storms snapped the cables. Julius Caesar improved the concept considerably in 55 BC. His engineers built a timber trestle bridge across the Rhine River in just 10 days, shocking Roman chroniclers. But Caesar's bridge required driving wooden pilings into the riverbed, which meant you needed slow-moving water, solid bottom conditions, and enough time to cut and shape timber on site. For deep, fast-moving rivers, the design was useless. Napoleon Bonaparte learned this catastrophically during his 1812 Russian campaign. When his Grande Armée retreated to the Berezina River in November, French engineers constructed 2 pontoon bridges to evacuate 40,000 troops ahead of pursuing Russian forces. They worked in waist-deep freezing water, building the bridges from salvaged timber and boats. The bridges held just long enough for Napoleon to escape, but at least 10,000 soldiers died in the crossing, crushed in panic, drowned when sections collapsed, or shot by Russian artillery while waiting their turn. The survivors described it as organized chaos, where a river crossing took 3 full days and cost more lives than major battles. World War I brought motorized vehicles and heavy artillery, which meant bridges suddenly needed to support far more weight than human engineers had ever calculated. British and French forces used steel pontoons, watertight metal boxes that could handle greater loads than wooden boats. But these pontoons weighed over 800 pounds each and required cranes to position. A typical World War I pontoon bridge across a 150-foot river needed 48 hours to assemble with a full engineering company, and that assumed no enemy interference. German forces at the Battle of the Marne in 1914 repeatedly destroyed Allied pontoon bridges with artillery before completion, proving that slow construction was a fatal vulnerability. By 1940, it was clear that the next war would be won by whoever could bridge rivers faster than the enemy could defend them. The old methods weren't just slow, they were obsolete. When German panzer divisions smashed through the Ardennes in May 1940 and reached the Meuse River, they brought prefabricated pontoon equipment that could be assembled in 8 hours. That speed advantage gave them the breakthrough that led to France's collapse in 6 weeks. The lesson was unmistakable. Speed in river crossings determined whether offensive momentum continued or died at the water's edge. The United States Army recognized this problem years before entering the war. In 1938, the Army Corps of Engineers began developing a new pontoon system specifically designed for rapid deployment under combat conditions. The M2 pneumatic pontoon represented a radical departure from traditional designs. Instead of solid wood or steel boxes, American engineers created inflatable rubberized canvas boats measuring approximately 15 feet long and 4 feet wide. The critical innovation was the multi-chamber design. Each M2 pontoon was divided into 5 separate air chambers. If enemy fire punctured one section, the other 4 kept the pontoon afloat. This redundancy meant a bridge could take damage and remain operational, something no previous pontoon system had achieved. When fully inflated using hand pumps, each M2 pontoon displaced roughly 99 cubic feet of water. According to Archimedes' principle, this meant it could support 2,800 pounds before the waterline reached the danger point. The engineering was elegant in its simplicity. More displacement equals more carrying capacity. But here's where the calculations became complex. A Sherman tank didn't weigh 2,800 pounds. It weighed 30 tons, which is 60,000 pounds. Engineers needed to calculate exactly how many pontoons could safely support that weight while accounting for the bridge deck itself, which added another ton per 30-foot section. The standard formula used displacement volume minus reserve buoyancy. You never wanted the pontoons more than 2/3 submerged because wave action and dynamic loading from moving vehicles could temporarily push them deeper. For a Sherman crossing, engineers typically spaced pontoons every 14 feet, requiring roughly 7 pontoons for a cement, 30-metre bridge. Each pontoon carried approximately 4.3 tons, well within safety margins under static conditions. But static weight was only part of the equation. When a 30-ton tank moves across a floating bridge at 5 miles per hour, it creates what engineers call a dynamic amplification factor. The pontoons at the crossing point dip deeper into the water, creating a bow wave that travels along the bridge structure. If that wave synchronized with the pontoon spacing, essentially hitting a resonance frequency, the entire bridge could begin oscillating. Soviet engineers learned this catastrophically during the 1943 Dnieper crossings, when improperly spaced pontoons created a harmonic wave that flipped 34 tanks into the river. The American solution involved cable anchoring systems that most people never notice in period photographs. Every pontoon bridge required upstream and downstream anchor cables attached to the riverbed or shoreline, positioned at precise angles calculated from current speed. The formula was straightforward. Faster current required steeper anchor angles and higher cable tension. In the Rhine, where spring currents reached 10 feet per second, engineers used 1-inch steel cables rated for 15 tons of tension, anchored at 45-degree angles every 50 feet. Those cables prevented the bridge from swinging downstream or developing the S-curve deformation that could collapse the structure. The physics were unforgiving. Miss the calculation by 5 degrees and the cables wouldn't hold. Space the pontoons incorrectly and harmonic waves could destroy the bridge. But get everything right, and you could move an armoured division across a major river in hours instead of weeks. By early 1945, American combat engineers had refined pontoon bridge construction into a precise science. Every movement had been practiced hundreds of times. Every component had been standardized to eliminate field modifications. Training facilities at Fort Belvoir, Virginia, and Fort Lewis, Washington, ran continuous 12-week courses where engineering battalions drilled pontoon assembly until it became muscle memory. Companies practiced on rivers with measured current speeds matching their deployment destinations. Slow water for Italy, fast water for Northern Europe. The foundation of rapid construction was rehearsal. The U.S. Army mandated that each engineer battalion complete at least 15 full bridge constructions before deployment, with the last 5 conducted at night under simulated combat conditions, including smoke generators and blank artillery fire. When the 291st Engineer Combat Battalion reached Remagen in March 1945, they had built practice bridges over the Chattahoochee River 47 times. Every soldier knew his exact role without requiring verbal orders. When German artillery hit, men scattered to pre-designated cover positions, then reassembled automatically once the barrage lifted. There was no confusion, no wasted time asking what to do next. Speed wasn't about working faster, it was about eliminating every wasted motion, every moment of confusion. The British took this principle even further, with time-competitive drills between engineering companies. The 51st Highland Division's engineers achieved the fastest recorded Rhine crossing in late March 1945, a 280-metre tactical bridge completed in 11 hours from first pontoon to first tank. Their technique involved pre-positioning all equipment on the west bank in specific sequence. Pontoons were inflated and arranged in order. Bailey panels were pre-assembled into 40-foot sections. Anchor cables were measured, cut, and coiled. When the order came to begin construction, there was no searching for parts or measuring on site. Everything was ready. The bridge crew moved like an assembly line, each man knowing exactly where the next component needed to go. The mathematics of current speed determined anchor cable angles, and engineers used pre-calculated tables rather than working out trigonometry under fire. For currents between 3 and 7 feet per second, anchor cables were set at 35 degrees from perpendicular. Between 7 and 10 feet per second, the angle increased to 45 degrees. Above 10 feet per second, common in spring melt conditions, cables went to 55 degrees with doubled tension ratings. These tables were printed on waterproof cards that every squad leader carried. No calculations required. Look at current speed, read the angle, set the anchors. Night construction presented unique problems that couldn't be solved by simply adding floodlights. Lights made perfect aiming points for German artillery. British engineers developed a blackout protocol using hooded flashlights with red filters that provided just enough illumination for close work without being visible from more than 300 feet. More importantly, they used white tape to mark every connection point on Bailey panels and pontoons. In darkness, engineers felt for the tape markers rather than trying to see the holes. This tactile system reduced assembly errors by 60% compared to unmodified equipment used at night. The 291st Engineer Combat Battalion reached the Rhine on March 8, 1945, one day after the Ludendorff Bridge was captured. Colonel Fraser's orders were simple and impossible. Build a pontoon bridge capable of supporting 40-ton loads across a 1,000-foot river while under artillery fire, and complete it before the railroad bridge collapsed. The first challenge was positioning. The bridge needed to be close enough to Remagen to support the bridgehead, but far enough downstream to avoid congestion at the captured bridge. Fraser selected a site 400 yards south of the Ludendorff Bridge, where the western bank had a gentle slope suitable for vehicle approaches. The eastern bank was steeper, requiring additional work to cut a ramp, but the current was slightly slower there, which mattered more than convenient terrain. Equipment arrived in a continuous stream. 25 2.5-ton trucks carried M2 pontoons, still deflated and packed in canvas bags. Another 15 trucks brought Bailey bridge panels, each weighing 270 kilograms. Steel treadway sections, anchor cables, hand pumps, connecting pins, timber for the approach ramps. The logistics were staggering. A single, heavy, tactical pontoon bridge required over 200 tons of equipment. Fraser's men began inflating pontoons at 0900 hours on March 9th. Each pontoon required approximately 30 minutes to inflate using two-man hand pumps. With 40 men working in rotation, they could prepare one pontoon every 7 minutes. The work was methodical and exhausting. Pump until your arms ache, switch positions, pump again. The goal was 40 pontoons fully inflated by nightfall. By 1500 hours, they had 28 ready. Then, German artillery found their position. The first barrage came without warning, 105mm shells that shrieked overhead and exploded in the shallows 50 yards from the assembly area. Fraser ordered everyone to cover. The men scattered to foxholes dug that morning specifically for this purpose. The barrage lasted 11 minutes. When it lifted, they returned to work immediately. 2 pontoons had been damaged by shrapnel. Not catastrophic, but it meant patching the rubberized canvas before those pontoons could be used. The patches were simple, essentially bicycle tire repair kits scaled up, but they took time. Every minute spent repairing was a minute not spent assembling. By nightfall on March 9th, they had 36 usable pontoons and had begun positioning the first sections in the water. The real work would begin at dawn. Construction of the main bridge started at 0340 hours on March 10th. Fraser divided his company into specialized teams. Team 1 positioned pontoons and connected them with steel pins. Team 2 laid Bailey panel sections across the pontoons, creating the bridge deck. Team 3 installed anchor cables, working from small boats to reach the riverbed attachment points. Team 4 handled approach ramps on both banks. The assembly sequence had been drilled hundreds of times, but executing it under combat conditions required absolute focus. The first pontoon went into the water at 0345 hours. Engineers waded into the Rhine, guiding the inflated pontoon into position against the current. The water was 42 degrees Fahrenheit. Within minutes, the men were shaking from cold, but they couldn't stop. Each pontoon had to be precisely aligned before the next one could be connected. The steel pins that linked pontoons together required perfect hole alignment. Miss by even an inch, and the pin wouldn't seat properly, creating a weak point that could fail under load. By 0600 hours, they had 7 pontoons connected in a line extending 60 feet from the western shore. Bailey panels were being positioned on top, creating the roadway surface. This is where the genius of Donald Bailey's design became apparent. Each panel measured 10 feet long and 5 feet tall, weighed 570 pounds, and could be carried by 6 men. The panels connected using simple pins that dropped through pre-drilled holes. No bolts, no welding, no complex engineering required on site. Just align the holes and drive the pins home with sledgehammers. The sound of hammering mixed with the roar of the current and the occasional crack of distant artillery. Fraser watched his men work with practiced efficiency. Every motion counted, every second mattered. By 0800 hours, they had 12 pontoons in the water with Bailey panels spanning the first 100 feet. Then German artillery found them again. This time the shells landed closer, exploding in the water between the partially completed bridge and the shore. Shrapnel peppered the pontoons. 2 men went down, wounded but alive. Medics dragged them to cover while the rest of the company continued working. Stop the entire operation for casualties, and you give German gunners time to adjust their aim. The doctrine was brutal but logical. Keep building, keep moving. Every pause increases the danger for everyone. One pontoon took direct shrapnel damage that punctured 3 of its 5 chambers. The pontoon began to sink. Engineers quickly disconnected it from the bridge line and pulled it to shore for repairs while a replacement pontoon was towed into position. The delay cost them 18 minutes. By 1,000 hours, they had 20 pontoons connected, extending nearly 300 feet from the western shore. The bridge was now far enough into the current that anchor cables became critical. Without proper anchoring, the Rhine's 8-foot-per-second current would push the entire structure downstream, tearing the connections apart. Engineers in small boats worked to position anchor cables at 45-degree angles upstream and downstream from each pontoon cluster. The cables, 1-inch steel rated for 15 tons of tension, were attached to concrete deadmen buried in the riverbed days earlier by divers. Getting the tension right required both calculation and feel. Too loose and the bridge would sway dangerously. Too tight and the cables might snap under dynamic loading. Fraser used a spring-loaded tension gauge, a simple device that showed green for correct tension, yellow for adjustment needed, red for catastrophic failure imminent. Every cable had to read green before the bridge could open to traffic. This is the work that never appears in dramatic retellings. Not heroic charges or desperate defences, but cold men in a cold river, adjusting cable tension with numb fingers while artillery explodes upstream. Yet, this was the work that won wars. By 1300 hours on March 10th, they were halfway across, 28 pontoons connected, 420 feet of floating bridge capable of supporting 30-ton loads. The eastern shore was still 580 feet away. Fraser checked his watch and calculated. At their current pace, they would complete the bridge by 2,000 hours, assuming no major interruptions. That was the optimistic projection. The realistic projection, accounting for German artillery and inevitable equipment problems, put completion at midnight or later. Either way, they would finish before the Ludendorff Bridge collapsed. They had to. 3 miles upstream, that railroad bridge was groaning under the weight of continuous tank traffic. Engineers had discovered cracked support beams that morning. The structure wouldn't last another week, maybe not another day. Everything depended on finishing these pontoon bridges. Not just Fraser's Bridge, but the 3 others under construction at different points along the Rhine near Remagen. The American breakout into Germany's industrial heartland depended on these floating bridges carrying the weight of modern warfare across a river that had defended Central Europe for 2,000 years. Fraser looked at his men, working in frigid water under intermittent artillery fire, and saw the future of military engineering. Not the construction of permanent monuments, but the rapid assembly of temporary solutions that kept armies moving forward. The war would be won not by the side with the strongest fortifications, but by the side that could cross rivers faster than the enemy could defend them. By 1600 hours, they had 34 pontoons in the water. The bridge stretched nearly 600 feet, less than 400 feet to go. The afternoon of March 10th brought a new problem that no amount of training could have predicted. At 1,620 hours, a German V-2 rocket, one of Hitler's desperation weapons launched from somewhere in the Netherlands, struck the town of Remagen 200 yards from the bridge construction site. The explosion shattered windows, collapsed a building, and sent debris raining down on the engineers. But worse than the immediate damage was what it represented. German High Command had decided that stopping the Rhine crossings justified using their most advanced weapons. The V-2 couldn't be intercepted. You couldn't hear it coming. One moment you were working on a bridge. The next moment everything within 100 yards was obliterated. Fraser gathered his officers. "We maintain pace," he said. "The V-2s are random. Artillery, we can predict and take cover. Rockets, we can't, so we don't try. We just keep building." It was the only rational response to an irrational weapon. By 1700 hours, 38 pontoons were in position. The bridge stretched 700 feet across the Rhine. Engineers on the eastern shore had begun work on the approach ramp, cutting into the steep embankment to create a graded path suitable for heavy vehicles. This was brutal manual labor, swinging picks and shoveling mud in terrain that hadn't been disturbed since the railroad bridge was built decades earlier. The work proceeded in shifts. 20 men cut and leveled for 30 minutes, while 20 more rested. Then they switched. It was the only way to maintain productivity without collapsing from exhaustion. Meanwhile, on the bridge itself, the final pontoon sections were being positioned. 42 pontoons now, 43. The gap narrowed with each addition. At 1,830 hours, with the sun setting behind the western hills, the final pontoon was connected. The bridge stretched 1,040 feet from shore to shore, supported by 46 M2 pneumatic pontoons spaced at precise intervals. Bailey panels formed a continuous roadway across the entire span. Anchor cables, properly tensioned and tested, held the structure against the Rhine's relentless current. Total construction time from first pontoon to final connection, 14 hours, 45 minutes. Fraser ordered the final inspections. Engineers walked the entire length of the bridge, checking every connection point, every pin, every cable anchor. The inspection took 1 hour. At 1,930 hours, Fraser declared the bridge operational. The first vehicle to cross was a 2.5-ton supply truck carrying ammunition for the troops on the eastern shore. The truck entered the bridge at exactly 1,940 hours, moving at the prescribed speed of 8 miles per hour. Fraser watched from the western shore as the truck proceeded across. The bridge deflected under the weight, dropping 6 inches at the midpoint, exactly as engineering calculations predicted. The pontoons rode lower in the water, but remained well above the danger threshold. The truck reached the eastern shore at 1,946 hours, 6 minutes to cross 1,000 feet. The bridge held. By 2,000 hours, a steady stream of vehicles was crossing. Supply trucks, ammunition carriers, jeeps, artillery tractors. The bridge carried exactly what it was designed to carry, the logistics of modern warfare. Then, at 2,130 hours, the first Sherman tank approached the bridge entrance. This was the real test. The M4 Sherman medium tank weighed 30 tons, fully loaded with ammunition and fuel. Every component of the bridge had been calculated to support this weight, but calculations on paper differ from reality. The tank commander received his instructions. Cross at 5 miles per hour. Do not stop on the bridge. Maintain steady speed to avoid creating harmonic oscillations. The Sherman's tracks bit into the Bailey panel roadway with a grinding metallic sound. The tank entered the bridge. Immediately, the structure deflected. The pontoons beneath the tank sank deeper into the water, displacing more volume to support the increased weight. The bridge dropped 18 inches at the Sherman's position, creating a visible depression that travelled along the span as the tank moved forward. Fraser held his breath. This was the moment when inadequate engineering revealed itself. If the pontoon spacing was wrong, if the anchor cables couldn't hold the dynamic load, if any single component failed, the entire bridge could collapse. The tank continued across. 100 feet. 200 feet. At the midpoint, the bridge deflection reached 24 inches. The pontoons were 2/3 submerged, right at the safety margin. But they held. The tank reached the eastern shore at 2,139 hours, 9 minutes to cross, no structural failures, no cable breaks. The bridge had successfully carried a 30-ton load across the Rhine. By midnight, 6 Sherman tanks had crossed Fraser's bridge. By dawn on March 11th, that number reached 38. The bridge operated continuously, carrying vehicles at calculated intervals to prevent excessive loading. Traffic controllers with stopwatches stood at the western entrance, releasing vehicles at precise intervals. 1 Sherman tank every 90 seconds, supply trucks every 45 seconds. The spacing was critical. Too close and the combined weight could overload the bridge structure. Too far apart and you wasted the bridge's carrying capacity. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But Fraser's Bridge was only one piece of the Remagen crossing operation. The 291st Engineer Combat Battalion, working simultaneously at a site 600 yards downstream, completed their heavy pontoon bridge on March 11th at 1,400 hours. This bridge, designated the Pershing Bridge after the newly deployed M26 Pershing heavy tank, used doubled pontoons to support loads up to 42 tons. The bridge measured 620 meters and consumed 51 pontoons with triple-stacked Bailey panels for additional strength. Construction time: 18 hours under, and continuous artillery harassment. The 51st Engineer Combat Battalion completed a third tactical bridge on March 12th. This was a lighter structure designed primarily for infantry and light vehicles, but it freed up capacity on the heavy bridges for tank traffic. By March 13th, 4 complete pontoon bridges spanned the Rhine at Remagen, with a 5th under construction. The engineering achievement was staggering. In 5 days, American combat engineers had constructed multiple bridges across one of Europe's most formidable rivers while under constant enemy fire. But the human cost was real and documented. The 291st Engineer Combat Battalion lost 47 men killed and 189 wounded during the Remagen bridging operations. German artillery destroyed 2 partially completed bridges, killing everyone on them. On March 12th, a German Arado 234 jet bomber scored a direct hit on a pontoon cluster, sinking 3 sections and cutting a bridge in half for 6 hours, while engineers worked under floodlights to repair it. The repaired section was operational again by midnight. The engineers didn't stop. They couldn't. Every hour without a functioning bridge meant supply trucks backed up on the west bank and troops on the east bank running low on ammunition. The mathematical reality of logistics was unforgiving. 25,000 troops required approximately 500 tons of supplies per day. Food, ammunition, fuel, medical supplies, replacement equipment. That meant 1,000 supply trucks crossing the Rhine every 24 hours. Without functioning bridges, the entire operation would collapse within 48 hours. On March 17th, 10 days after its capture, the Ludendorff Bridge collapsed into the Rhine. Engineers had known it was coming. The structure had taken damage from German demolition charges during its capture, sustained near-miss bomb hits during Luftwaffe attacks, and carried far more traffic than its 1916 design could handle. At approximately 1,500 hours, rivets in the main support truss began snapping spontaneously. A vertical hanger fell. The entire center span dropped into the river within seconds. 28 American engineers were killed in the collapse, working on repairs at the moment of failure. Another 63 were injured. 18 of the dead were never recovered, presumably drowned in the Rhine's swift current, but by then it didn't matter strategically. The pontoon bridges were operational and carrying the full logistics load of the breakout. When the Ludendorff fell, 6 Sherman tanks were crossing Fraser's pontoon bridge. They continued across without incident. The pontoon bridges absorbed the traffic that the railroad bridge could no longer carry. By March 25th, the 6 pontoon bridges at Remagen had carried 11 divisions, roughly 125,000 men and 20,000 vehicles, across the Rhine. The bridges operated 24 hours per day, with maintenance performed during brief windows when traffic was light. Damaged pontoons were replaced without shutting down the bridge. Engineers simply disconnected the damaged section, floated a replacement into position, and reconnected the structure. Average downtime for pontoon replacement, 14 minutes. The bridgehead that these pontoon bridges supported became the staging ground for the final Allied drive into Germany's industrial heartland. Those bridges, built in hours under artillery fire, changed the timeline of the war's end, but Remagen was only one crossing. The success there influenced Allied strategy across the entire Western Front. On March 22nd, General George Patton sent his Third Army across the Rhine at Nierstein without waiting for the elaborate preparations that characterized other crossings. Patton's engineers used DUKW amphibious trucks, Navy landing craft, and pontoon ferries to get infantry across. By late afternoon on March 23rd, engineers had completed a 40-ton treadway bridge. Construction time, 16 hours. Patton, who despised his rival Montgomery, deliberately announced his crossing to the press at a time calculated to steal attention from Montgomery's Operation Plunder, the massive set-piece Rhine crossing scheduled for March 23, where Montgomery planned to use 4,000 artillery pieces, bomber support, and airborne troops. Patton crossed with pontoon bridges and determination. Both approaches worked. But Patton's proved faster. Operation Plunder itself demonstrated the culmination of Allied bridging capabilities. On the night of March 23, the 17th Armoured Engineer Battalion constructed a tactical bridge near Wesel, using M2 treadway and 93 pneumatic floats. Bridge construction started at 0945 hours. By 1600 hours, the first truck crossed the floating pontoon bridge. Over 1,150 feet of bridge laid in 6 hours, 15 minutes. It was record-setting for that size of structure. 25 trucks, each carrying 2.5 tons, transported the bridge components to the construction site. The kill zone was precisely defined. German artillery positions in the hills surrounding Wesel had direct line of sight to the crossing. Engineers worked in 2-hour shifts, partly because of exhaustion, but mostly because anyone working longer than that had a statistically significant chance of being hit. The 17th Armoured Engineer Battalion suffered 12% casualty rates during construction. 1 man in 8 was wounded or killed before the bridge was complete. Medics worked directly alongside engineers because waiting for the wounded to be evacuated would slow construction to a standstill. Soviet engineering doctrine during the same period emphasized speed through sheer numbers rather than perfection. During the Vistula-Oder offensive in January 1945, the Red Army threw entire battalions at river crossings simultaneously. While one company assembled the main bridge, 2 others constructed parallel footbridges for infantry. A 4th company pre-built bridge sections on the near shore. When German artillery destroyed sections, and it always did, replacement sections were already assembled and waiting. Soviet Marshal Georgy Zhukov calculated that redundancy was faster than perfection. Build 3 bridges simultaneously, and even if 2 are destroyed, 1 gets through. The approach resulted in horrific casualties. Soviet combat engineers, called sappers in Red Army terminology, faced casualty rates exceeding 60% during some river crossings. The Dnieper River crossings in 1943 cost some sapper battalions more than half their strength. Stalin's calculation was brutal but logical from a strategic perspective. A sapper battalion numbered 450 men. Losing 270 of them to secure a crossing for 3 rifle divisions, 45,000 troops, was considered acceptable. American and British forces operated under fundamentally different doctrine. U.S. engineer battalions at the Rhine suffered roughly 8% casualties during bridge construction, terrible by peacetime standards, but dramatically lower than Soviet rates. The difference came from 3 factors: superior counter-battery fire that suppressed German artillery, smoke generator units that obscured construction sites, and, most importantly, a rehearsal that reduced time in the kill zone. The rehearsal factor cannot be overstated. Units that trained for months before deployment had survival rates 40% higher than hastily assembled units thrown into combat without proper preparation. The U.S. Army's 1946 analysis of engineer effectiveness concluded that every additional week of training reduced combat casualties by 4%. The investment in training camps, rehearsal facilities, and professional schools wasn't humanitarian sentiment. It was cold calculation. Trained engineers completed bridges faster and died less often, both of which served military objectives. The technology that made rapid pontoon bridge construction possible didn't disappear after World War II. The M2 pneumatic pontoon and Bailey Bridge panel system became the foundation for all subsequent military bridging equipment. When North Korean forces invaded South Korea in June 1950, U.S. Army engineers arrived with the same Bailey panels their predecessors used at Remagen. The Naktong River crossings in August 1950 relied on Bailey pontoon combinations that differed only in minor details from Rhine crossing designs. The modular system proved so adaptable that American forces used Bailey bridges throughout the Korean War, constructing over 400 of them. The Vietnam War saw Bailey principles evolve into the medium girder bridge system adopted by US forces in 1965. The MGB used aluminum instead of steel, reducing panel weight from 270 kilograms to 140 kilograms, but retained Bailey's core concept. Identical interchangeable components assembled without specialized tools. The modern US military uses the improved ribbon bridge, introduced in 1985 and still in service today. The IRB consists of modular bay sections, each 6.7 meters long, carried on a 5-ton truck. A combat engineer company can deploy a 100-meter bridge in 30 minutes using 8 bay sections, connecting them while floating on the water. The IRB can support Monet Abrams tanks weighing 62 tons, nearly double what World War II bridges handled. But examine the IRB's design principles and you find the same concepts. Modular sections, standardized connections, assembly requiring only basic hand tools and trained crews rather than specialized equipment, NATO standardization agreements established. In the 1970s, mandate that all member nations' military bridging equipment must be intercompatible. British, German, and American bridge components can connect to each other, allowing multinational engineering units to pool resources during operations. This interoperability doctrine stems directly from Rhine crossing experiences, where hybrid bridges successfully combined Allied and captured German equipment. Modern military engineers still study the Remagen operations as the gold standard for rapid tactical bridging under combat conditions. The U.S. Army Engineer School at Fort Leonard Wood teaches Rhine crossing case studies to every combat engineer officer. British Royal Engineers study the 51st Highland Division's 11-hour bridge as an example of perfect execution. The specific equipment has changed, but the engineering philosophy remains identical. The civilian world adopted these military innovations more slowly, but just as thoroughly. After World War II, surplus Bailey bridges found second lives across Africa, Asia, and South America. The Australian Army donated Bailey equipment to Papua New Guinea in the 1960s, where some bridges remained in daily civilian use until the 1990s. The simplicity that made Bailey bridges work for wartime armies made them ideal for rural infrastructure in regions without heavy construction equipment. Modern disaster relief organizations maintain Bailey bridge stockpiles specifically for emergency deployment after earthquakes, floods, or infrastructure collapse. When the 2010 Haiti earthquake destroyed Port-au-Prince's road network, international relief teams airlifted Bailey bridge components and had 3 major crossings operational within 72 hours. The 2011 Tohoku earthquake in Japan saw military engineers deploy modular bridges based on Bailey principles to restore coastal access roads. The design that won World War II continues saving lives in peacetime emergencies. But the most profound legacy isn't technological, it's doctrinal. The understanding that speed in river crossings determines whether offensives succeed or stall at the water's edge. That training and rehearsal save more lives than courage alone. That temporary solutions deployed rapidly often matter more than permanent structures built slowly. Colonel Harvey Fraser returned to the United States in November 1945 and spent the next 20 years training new generations of combat engineers. He died in 1968, largely unknown outside military engineering circles. His obituary in the Corps of Engineers newsletter mentioned his work at Remagen in a single sentence. But the bridge he built in 14 hours under artillery fire carried more traffic than some permanent bridges carry in decades. The pontoon bridge technology that Fraser's battalion employed wasn't revolutionary. The Romans built floating bridges. The Persians built floating bridges. What was revolutionary was the speed, the carrying capacity, and the understanding that modern mechanized warfare demanded solutions that could be deployed in hours, not weeks. The mathematics of buoyancy, the physics of dynamic loading, the engineering calculations for cable tension, all of this had been understood for decades. What changed in World War II was the realization that these principles needed to be applied faster and under worse conditions than anyone had previously thought possible. The M2 pneumatic pontoon weighed less than civilian boats but supported more weight through better design. The Bailey bridge panel looked simple because simplicity was the design goal. Every component was engineered to be carried, connected, and deployed by ordinary soldiers with basic training. No specialized equipment, no complex mathematics required in the field. Just straightforward assembly of well-designed parts. This represented a fundamental shift in military engineering philosophy. Previous bridge designs tried to be permanent or semi-permanent, structures that would last for months or years. World War II bridges were designed to be temporary, to last just long enough to get the army across, and then perhaps be disassembled and used somewhere else. The impermanence was intentional. A bridge that takes 2 days to build and lasts 2 weeks is more valuable in mobile warfare than a bridge that takes 2 weeks to build and lasts 2 years. By March 1945, Allied combat engineers had internalized this principle completely. The goal wasn't to build the strongest bridge or the most elegant bridge. The goal was to build a bridge fast enough that the army kept moving. Everything else was secondary. The German army never fully adapted to this reality. German engineers built excellent permanent bridges. Their pontoon equipment was robust and well designed. But German doctrine still emphasized durability over speed. A German pontoon battalion could build a magnificent bridge that would last for months. An American pontoon battalion could build an adequate bridge in 1/3 the time. In mobile warfare, adequate and fast beats magnificent and slow. This is why the Remagen crossing mattered beyond its immediate tactical significance. It proved that rapid bridging under combat conditions wasn't just theoretically possible. It was practically achievable with proper training, equipment, and doctrine. The 6 divisions that crossed the Rhine at Remagen didn't wait for perfect conditions. They crossed on bridges built in hours while under fire, bridges that swayed in the current and deflected under load, but held together long enough to change the course of the war. The legacy extends into modern military operations. When US forces invaded Iraq in 2003, combat engineers bridged the Euphrates River using technology that would have been recognizable to Colonel Fraser. Modular pontoon sections, Bailey-style panel bridges, anchor, cables calculated from current speed. The equipment was more modern, the materials lighter and stronger, but the fundamental principles remained unchanged. Speed matters. Training matters. Simplicity in design allows complexity in application. Every modern military maintains specialized bridging units, specifically trained for rapid river crossings under combat conditions. These units drill constantly, practicing bridge construction in all weather conditions, at night, under simulated fire. The muscle memory that saved lives at Remagen is still being instilled in combat engineers today. The understanding that every second of construction time in a kill zone increases casualties drives training intensity. Engineers who can assemble a bridge section in 12 minutes instead of 15 aren't just 12% more efficient, they're 20% more likely to survive. The mathematics of combat engineering are written in blood and bridge pins. Donald Bailey's contribution to this story often gets overlooked because pontoon bridges seem less innovative than Bailey's panel system. But Bailey panels wouldn't work on rivers without pontoons to support them. The combination of Bailey panels for the bridge deck and pneumatic pontoons for flotation created a system that was greater than the sum of its parts. You could build a Bailey bridge faster than any previous fixed bridge. You could deploy pontoons faster than any previous floating bridge. Combine them, and you could bridge major rivers in hours. The engineering synergy between these two systems changed warfare. Rivers, which had been absolute barriers requiring days or weeks to overcome, became temporary obstacles that delayed advances by hours rather than weeks. This shift in timeline fundamentally altered how armies planned offensives. Before World War II, river lines were natural stopping points where offensives paused while engineers built crossing infrastructure. After World War II, rivers were just another terrain feature to overcome quickly and move past. The operational tempo of modern warfare increased dramatically because engineers could maintain logistics flow across rivers without breaking offensive momentum. The Rhine crossings of March 1945 proved this concept at scale. Multiple divisions crossed multiple rivers simultaneously, using rapidly deployed temporary bridges. The German army, fighting a defensive campaign, couldn't destroy bridges faster than Allied engineers could replace them. Every destroyed bridge was replaced within 24 hours. Often within 12 hours, the Wehrmacht learned what Persian, Roman, and Napoleonic armies had learned before them. You cannot stop an enemy who can cross rivers faster than you can destroy crossings. By April 1945, German forces had abandoned attempting to defend river lines in western Germany. They fell back to prepared positions on the far side of rivers, ceding the crossings to Allied engineers who built bridges while German forces were still retreating. The tactical decision made strategic sense. Why waste artillery ammunition destroying bridges that will be replaced within hours? Better to fall back and establish defensive positions with better fields of fire. But this decision also meant that the Allied advance into Germany accelerated in April 1945, far beyond what German High Command thought possible in January. Rivers that should have provided defensive barriers lasting weeks provided delays of mere hours. The timeline of Germany's collapse was directly affected by the speed of Allied river crossings. Historians debate how much the war was shortened by various factors: strategic bombing, Soviet offensives from the east, collapse of German industry, Allied air superiority. But few question that rapid bridge construction shortened the war's endgame by weeks, possibly months. The Rhine crossings in March allowed Allied forces to encircle the Ruhr industrial region by mid-April, capturing hundreds of thousands of German troops and eliminating Germany's remaining industrial capacity. Without those rapid crossings, the encirclement would have taken significantly longer, allowing more German troops to escape east and extending the conflict. Every week the war continued cost thousands of lives. Allied casualties, German casualties, civilian casualties in both Germany and the remaining occupied territories. The bridges at Remagen, built in hours by combat engineers working in freezing water under artillery fire, saved lives by ending the war sooner. That's the calculation military engineers made then and make now. Speed in construction equals speed in victory equals fewer total casualties. It's cold logic applied to the hottest circumstances, men building bridges in the middle of battles because mathematics and training say this is how wars end faster. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.